Welcome to this short video on solving the harmonic oscillator in 2 dimensions using polar coordinates. This video is going to serve as an intermediate step towards the solution of the more interesting cases where we implement gravitational forces. Before we jump into the specific case of the harmonic oscillator in 2 dimensions solved in polar coordinates instead of the standard Cartesian coordinates, which we have looked at in the discussions we had on the harmonic oscillations, let us quickly remind ourselves about some of the findings which we got last week and the week before. So one of the things which we did was to define the relative and center of mass coordinates. So the center of mass coordinates, which we wrote with this uppercase R, is given by the weighted sum of the different positions multiplied with their respective masses divided by the total mass m. The other quantity which we defined was the relative position, which is defined in terms of R1 minus R2 here. So we are focusing mainly on a 2-particle problem. And however, this type of formalism which we're setting up here is not limited to 2 particles only. This is something which we can extend easily to the case of many more objects. And as you will see in the second midterm, where we're going to look at the gravitational problem applied to the solar system, you're going to have to deal with all the planets. The other thing which we did was to define a new system. So one of the definitions which we put up was to define the so-called center of mass system. And this is a pretty common definition, which is used in many physics applications. This goes from the kind of gravitational force problems which we are studying here to, for instance, the typical scattering problem. So this is normally called the center of mass frame. So I'm going to use a COM as a shorthand for center of mass. And this is simply called the center of mass frame. And you're going to encounter this in many other different physics courses. Now, this simplifies our formalism quite a lot. One of the things which we also observed was that the total linear momentum, which is now the sum of all the single momenta as a derivative as a function of time, is equal to 0, which means that P is a constant, and we say this is conserved, and it's a constant of the motion. We also define this P, the total linear momentum, to be given by the total mass multiplied with the time derivative of the center of mass position. Now, another thing which we found when we looked at this problem in the center of mass frame is that when we looked at the total angular momentum, which is now defined as R, and it's a cross product with a momentum P. And in this specific case, we are not looking at the specific definition of it in terms of the coordinate system which we have, or the number of particles which we have. But one of the things which we found then last week is that the angular momentum, if we have internal forces only, is equal to 0. So it means that it has no torque, and it means that the angular momentum is conserved. And that means it is a constant of the motion. Now, when we then use this fact that the angular momentum is conserved, it means that when we look now at a plane which is spanned by the vectors R and P, we know that since the angular momentum is defined as the cross product of these 2 vectors, we could easily define the angular momentum to be in the z direction, and x and y, in this case of relative coordinates, would then define the x and y plane. And we could think of the motion taking place in the x and the y plane. So we can now reduce the problem to a 2-dimensional problem. And when we are in 2 dimensions, the thing which is going to be pretty powerful when we now want to solve the gravitational force problem is that when we make a transformation from Cartesian coordinates with x, y, and z to polar coordinates or spherical coordinates, we can actually find an analytical solution to a two-body problem. And this is a rather unique result, which is not easy to obtain for other types of physics forces. So in our case now, when we look at the definition of R, what we have is that R is given by X multiplied with the unit vector in the X direction plus Y multiplied with the unit vector in the Y direction. We define R, and since these are now polar coordinates, to be defined from 0 to infinity. The angle phi is defined to be between 0 and 2 pi. Then, when we did this, we could then rewrite, for instance, the kinetic energy and also the equations of motions in terms of the polar coordinates. So what we have now is that X is given by R times cosine phi, and Y is given by R times sine phi. Then what we found is that the kinetic energy could now be rewritten in terms of the first derivative of the relative position. So R here now is the relative position. Actually, it's absolute value. And we have that K is given by 1/2 times the reduced mass, where we have defined the reduced mass as M1 times M2 divided by total M. And let me quickly remind you that R is given by X squared plus Y squared. So this is actually the magnitude of the position of a given system in terms of relative coordinates only. So we would then have the time derivative of R squared plus R squared multiplied with the time derivative of phi squared. So this is the way the kinetic energy looks like when we make a transformation to polar coordinates. So remember that we could make this transformation to a two-dimensional system because angular momentum is conserved. We put the central mass to be equal to 0, the central mass position. So that means that we are placing ourselves in the central mass frame, which is nothing but a redefinition of our origin. And we can do this because the force which we have, or the potential, is what we normally call translationally invariant. So if we translate the system, the potential itself, which depends only on the absolute value of the distance between two objects, is going to be invariant towards the transformational origin. So it's pretty common to then define the central mass frame, which often simplifies our mathematics. So when we did that, and before we move on, let me quickly remind you that this R dot is simply d of R dt, and phi dot is the same as d phi dt. So I'm going to use this kind of shorthands on here. Now, the next thing we found, so let's put this up here, is that we had a differential equation for phi dot, which is given in terms of the angular momentum divided by the reduced mass and divided by R squared. Then the other differential equation, which is now a second order differential equation in the absolute value of the relative position, this is now given by the applied force, but now only its R component plus an artificial term, since we made a transformation to polar coordinates. We are operating with relative coordinates only, and we could rewrite this in terms of an artificial term, which we use to define a so-called effective potential. So this led to the definition of what we had defined last week as an effective potential, V of F of R, which is now given by the original potential, which actually depends only on the relative distance and its magnitude, plus L squared divided by 2 times mu times R squared. And you see now that when we look at the definition of the force, its R component, this is given by minus d of V of R, d of R. And it's easy to convince yourself that, and this is actually this effective potential. So let's just put that one up here. That's V of effective. And if you look at the definitions here, this is now the same as this minus d of d of r, v of r, where we need to specify the specific potential here. And then we have plus L squared divided by mu times r cubed. So this is now our new effective force due to the way we have made these transformations. Now let's take a look at the harmonic oscillator again. So we have been looking at the harmonic oscillator in 1 and 2 dimensions when we discussed harmonic oscillations in Cartesian coordinates. And we know that we can find easily the analytical solution of the problem. So if we now switch to the harmonic oscillator, and we're going to use this as a warm-up case for what is going to come with the gravitational force. So in the harmonic oscillator, what we have is a potential V of r, which is given by 1/2 of k, our constant, times r squared. And this is the same as 1/2 of k times x squared plus y squared. Now, if we now take a look at the equation of motion for this specific case, we know that now the force is given by the derivative with respect to this potential, plus this artificial term, which we normally call an orbital barrier because it's given by the orbital angular momentum. If we now go back to the equations which we had, we see now that we can plug these equations in and simply calculate the derivative of the force. So what we would get in this case is that we would have a mu of r dot, which is simply given by minus k times r. And then we would have this additional term, which goes like L squared divided by mu of r cubed. In addition, what we have is another differential equation which we need to solve, which is due to the fact that the angular momentum is conserved. And this is given simply by L divided by mu, the reduced mass, and r squared. Now, if you look at the equations in polar coordinates, and you want to make a comparison with the corresponding equations in Cartesian coordinates, so if we go back to what we discussed in connection with harmonic oscillations, if we now just stayed in x and y, so we're dealing with Cartesian coordinates, then what we would have then would be the differential equations in terms of m or mu, or relative mass here, but let's just simply write this as m. What we will have then is a d of x of dt. And this would simplify because now we don't have this artificial potential which we add, which is given in terms of the angular momentum. We would have a corresponding equation for the y degrees of freedom, which is given by minus k times y. Now, these will be the corresponding equations if we now simply looked at the problem in Cartesian coordinates. And this m is the same as the reduced effective mass which we have. Now, the thing we should note here is that the equations in Cartesian coordinates, so the xy equations, they are what we call separable. They are not coupled. Are separable in x and y. So this means that when they are separable, the differential equations are not coupled. So you can see now that the equation for x does not depend on y, and the same happens for the equation for y, which does not depend on x. And we found that the solution then could easily be written down in terms of a constant a times a cosine. We have this natural frequency omega 0 plus a b times a sine of an omega 0 times t. And similarly, we would have a solution for y, which is now given by a constant c to be determined by the initial conditions times an omega 0 of t plus a new constant d multiplied with sine of omega 0 of t. So when we deal with the harmonic oscillator, one of the things which you may note here is that we should rather solve the equations in Cartesian coordinates because x and y do not depend on each other in the equations. So when you now move over to polar coordinates and the transformation which we have done now, our harmonic oscillator looks a little bit different. So this will be the equation of motion for the relative coordinate. So this will be the acceleration for the relative coordinate. And this will be the angular velocity which we have. Now, in this particular case, the equations, they depend on r. So r is not an equation which depends only on one of these equations, but there is actually a connection between the equation for the acceleration in the direction of the radial coordinate and the angular velocity. So these two equations here are equations which we normally then call for coupled differential equations. This means that the problem in Cartesian coordinates is an easy one to solve because the equations are not coupled. Whereas when we move to polar coordinates, the equations are coupled. So the harmonic oscillator is a case where we don't gain anything by moving to polar coordinates. So I want you to keep this in mind because this is one of the motivations for why we actually make this transformation to either polar coordinates or spherical coordinates for the gravitational force. In case of the gravitational force, when you go back to homework number 5, when you studied the Earth-Sun case, what you noted then was that your equations, when you wrote them out in Cartesian coordinates, which is normally the easiest way to write the equations when you want to solve them numerically, they had equations which were coupled. So we could not disentangle x and y by themselves in just a neat, nice equation, as we are doing here in the harmonic oscillator. So for the gravitational force, running the calculations in Cartesian coordinates and wanting to find an analytical solution is not possible. Rather, the transformation to polar coordinates is the one which makes life much, much easier for us. However, one of the reasons why we are looking at this harmonic oscillator case is that there are many small insights which we can carry with us when we are looking at the gravitational force problem. And one of these small insights deals a little bit with how we're going to analyze the problem. Before we proceed with these analytical analysis of the harmonic oscillator in 2 dimensions in polar coordinates, let's just make a quick plot of the system. So what we're going to do now is to make a plot of the harmonic oscillator potential plus this effective potential, which comes from the angular momentum. So again, keep in mind that this is a term which you get in addition because you're making a transformation from Cartesian coordinates to polar coordinates. But it allows us to make a plot in 1 dimension with only r and study the potential, and from the potential, try to figure out what kind of motion we may expect. Now, what you see here in the lecture notes from last week and also from week 12, which is this week, we have a simple code which makes a plot of this harmonic oscillator potential with the angular momentum. And we've chosen an initial value for x, 0.5, and a final one for 3. So this is our initial and final values for r. We put k equal to 1, m equal to 1, just to simplify life, put the angular momentum to 1. So these are just parameters which we picked here in order to make life a little bit simpler for us. We set up an array of the values which we want to have along the x-axis. And with that, we now define a potential, which is 0.5 times k times x squared plus the angular momentum part, which you see here. And then we make a plot. So you can see from the motion here that you can now repeat many of the same kind of analysis types, which we looked at in the first midterm and in several homeworks. So you could ask yourself what happens now if I'm just down at this point here, where we are at the bottom of the potential. What kind of motion do we get from that? Or if I place myself, let's say, at an energy which corresponds to a potential which is equal to 2, I would then expect from the kind of analysis we have made that we would simply start here with 0 kinetic energy. It would just go down to the potential well bottom, and then it would move up again to the same energy of 2 here to another value of R, and then it would oscillate back and forth. So how does this motion, which we now are trained to look at in 2 dimensions in terms of Cartesian coordinates, how can we now interpret this minimum here of the potential, which is now is given in terms of the polar coordinates only? Keep in mind also that the potentials, and this applies to many of the potentials you will encounter in physics, they do not depend on the angle phi which we have. We say that the potential is then isotropic. It takes the same value irrespective of orientation in space. So this leads to another important symmetry. One of the symmetries is actually that angular momentum is conserved. Now let's do some paper and pencil analysis with the parameters of this potential here, and see if we can gain some kind of deeper insights, and then go back to the plot of this potential here and see if we now can understand what kind of motion we may expect from the potential at this point where it has its minimum. Now, one of the things we are doing now is to make this paper and pencil analysis of the harmonic oscillator potential. So we have a potential now in polar coordinates, which looks like this. So we have 1/2 of k times r squared, and then we have this term, which is due to the angular momentum. Now, one of the things we could ask now when we make the plot of this potential, as we saw from the Jupyter notebook, this potential looks something like this. And we're asking ourselves now, what is the value for R at the minimum here? So this is our V of R. Now, to find the value at the minimum for this effective potential, and we should be a little bit careful when I'm writing this potential here. So instead of writing V of R, we should actually write this as a V effective of R to be more precise. So this is a V effective of R, and this is the V effective again. So what we would do now is simply to calculate the derivative of this function and require that that one is equal to 0. So that gives us clearly k times r minus L squared divided by mu of r cubed. That means that we can now find the minimum value for r. So this r min here. So we have an r min then, which is simply given by L squared divided by k times mu, and this is to the power of 1 divided by 4. Now this has some interesting consequences for us now. So let's look at the value for the energies which we have. So one of the things which we could calculate is the total energy at this minimum point. So we know that the total energy is given by kinetic energy plus the potential energy. And in our case, this potential energy has to be translated into this effective potential energy. But we have to be a little bit careful here, because the way we write these equations, they're given now in terms of the real potential, not the one which depends on this angular momentum term. So you have to remember also that k, this is one of the results we found last week, is given by 1/2 of mu. So this is given by V of x squared when we are now in 2 dimensions. And when we rewrote that one in terms of the polar coordinates, this became equal to an r dot squared plus an r squared times a phi dot squared, like this. And we know that the potential energy, when we now do not add this angular momentum term, is given by k times r squared. Now, one of the things which we can do then is simply to ask ourselves, what is the value of the potential energy at the minimum? So what we get then, when we now plug in things, and note well that this phi, which we have here, phi dot, is actually given by L divided by mu of r squared. So this means that when we now rewrote the potential in terms of an effective potential, when we look at the energy, this is given by 1/2 of mu times r dot squared. So this is the velocity in the radial coordinate. So we would call this a radial velocity. So let's just rewrite that one as a radial velocity. And what we note then is that this can now be rewritten in terms of the effective potential. So this means that this effective potential gets a term which comes actually from the kinetic energy. So this term is given now by 1/2 the original potential of r squared plus this effective potential which we have, which is now given in terms of L squared. So this should actually be an L, just a single L. So this is given in terms of L squared divided by mu. And this is again divided by r squared. And it has a factor which comes like, so we have a square here of 1/2 times mu. So this factor becomes equal then to, at the end, we get an expression which runs like 1/mu of r squared plus the effective potential, which is a k of r squared plus L squared divided by 2 times mu times r squared. So the last terms here, they define now actually this effective potential. So the kinetic energy term gives to the effective potential a term which now depends on the angular momentum. So these terms come actually from the kinetic energies. But since we are interested in separating out the radial velocity from the rest of the equations, we end up by defining an effective potential. So it comes actually from kinetic energy. Now, if we now go back and look at the value at this minimum, so if we plug in the value which we found here for the minimum, this specific value here, we can now plug that into the equation for the energy. So that means that we need to evaluate this r squared min. And we know that that is going to be equal to L divided by the constant k times mu. And then I can now calculate this effective potential. So what I will find out then is that my effective potential is going to be given by V of F at R min. That takes the value, when we do the algebra, of L times an omega 0. And this omega 0 is simply given by the values which we have seen before. It's K divided by mu. So it contains an angular momentum term multiplied with the frequency which we have defined as the natural frequency of the system. So it means now that the total energy at this R min is given by the kinetic energy, which we haven't defined yet. We don't know the value of R dot squared, but this has to be calculated at the minimum value. So this must be at R min plus, so let's rewrite this in a better way. So we should rewrite this now in terms of the following. So we have a d of r dt squared defined at r equal to r min plus L times omega 0. And now we come to the differential equation, which we have for the radial equation. So we have now a mu of r dot, and we know that this one is equal to the potential and the force which is applied in the r direction, F of r, plus L squared divided by mu and r cubed. Now, if we now bring back the equations which we had for the harmonic oscillator, this is equal to minus k times r plus L squared divided by mu times r cubed. And now we can ask ourselves, what is the value of this quantity here at the minimum? So what we're asking ourselves now is, what is the value of the second derivative of r of dt evaluated at r equal to r min? Now, if we look back at what we found earlier, when we look at this equation minus k of r plus L squared divided by mu of r cubed, if we go back a little bit, we found that r min is given by having the derivative of the effective potential with respect to r equal to 0. So what we see now is that these two terms cancel each other. In this case, we have kr positive and we have a minus here. If we now scroll down the equation, we see that this is basically the same equation. So it means that at the minimum value, what we have then is that this quantity is actually equal to 0. So that's an extremely useful result. So what it tells us now is that the acceleration is actually equal to 0. So we have 0 acceleration. And that means that we have a constant velocity. Another thing which is very important for us, if we now look at this function phi, the derivative of phi, the angle d phi dt, we know that this one is equal to L divided by mu of r squared. And if we now plug in the value at the minimum for r, what we find then is that this is actually given by the natural frequency of the system. So it means that the angle phi moves also at a constant velocity. So if we make a plot here with a center here, so this would be our r min. And then we have an angular velocity. So this angle phi moves at a constant velocity. So we have a d phi dt, which is given by the natural frequency of the system. So what this system is actually going to span now, since the acceleration in the radial direction is equal to 0, it means that the velocity is a constant. If the velocity is a constant, the motion is going to be a circle. So this is the closest I get to a circle when I make my drawings. So motion in a circle, with constant velocity, constant radial velocity, which is now d of r dt, and constant angular velocity. Of d phi dt. So what we have showed now, when we have made this transition or this transformation to polar coordinates, when we now go back to the way we plot the potential, which is an effective potential, what we have then is a minimum here, which now corresponds to a 0 acceleration in the radial direction, which means that we have a constant radial velocity. And we have also, due to the conservation of angular momentum, we have a constant angular velocity. So at the minimum here, the motion is now going to be a circular motion. So this leads to a circular motion. And that's a pretty interesting observation. What we're going to note is that, and we're going to see this a little bit later, if we were to place ourselves at this initial position with, say, 0 initial velocity, then we will simply go back and forth between these positions. And the motion then is, as we will see in just some few lectures, this is going to correspond to an elliptical motion. So what we have now is a case where we have placed ourselves at the bottom of a potential in polar coordinates with a radial dependence only, and that corresponds to a circular motion. And we are going to see the same when we now apply the gravitational force.